Okay, so problem 1. A random sample of 29 with a sample mean equal to 188.6 and a sample standard deviation equal to 42.8. By the way, that means we're going to have a t distribution because if we have sample standard deviation, that's going to go with t. And I'm going to get the standard error. Sx bar is equal to s divided by the square root of n. So that's the 42.8 divided by the square root of 29, and that comes out to be 7.95. Can we conclude that the population mean differs from 173? So the research hypothesis is mu not equal to 173. And HR then will be mu equal to 173. And make sure you get that. If it differs, it's a two-tailed test. So for the critical value approach, we're going to reject HO if t-test, again it's a t-test because we have sample standard deviation. If it's greater than, so we have alpha is 0.5, it's two-tail, and degrees of freedom is going to be 28. That's just 29 minus 1. The degrees of freedom is 29 minus 1, or n minus 1. This is going to be 2.048, or if it's less than minus 2.048. So the t-test is equal to the statistic, x bar, minus the hypothesized mean, over the standard error. So that's equal to 188.6 minus 173 over 7.95. So we get 1.96. That just means that the value we observed, the 188.6, is almost 2 standard errors above the hypothesized value of 173. Anyway, that's not greater than 2.048, and it's not less than minus 2.048. Therefore, we fail to reject HO, and we conclude that mu could be 173, or at least this, we could not rule that out as a possibility. The difference that we observed there between 188.6 and 173 could be a reflection of sampling error, not indicative of a real difference between a real difference such that we would conclude that mu is not equal to 173. I think the biggest mistakes on this one had to do with really setting up the hypotheses. Quite a few people, or at least some people, set that up as a mu greater than one-tailed test when it clearly says differ. Okay, quite a few people had problems with this next one, certainly more than I had anticipated. And a few people made it, I think, a little more difficult than it needed to be. Well, let's start with, if you just write down the information from the problem. We have a population mean of 960. We have a population standard deviation of 285. We have a sample size of 25, which, even though this says that it's skewed, since we're asking about sample means, we have a sampling distribution, the skew doesn't make any difference because our sample size is greater than 15. And it asks to find the probability of a sample mean, find the probability of a sample mean greater than 11. So we're going to have a sampling distribution of x bar. We know it's a bell curve because n is large enough. It's 25, and we have somewhat skewed, but just a little skewed. We're going to assume we don't have outliers or extreme values. The mean of this sampling distribution is equal to the mean of the population, or 960. And we need to get the standard error for this. It's sigma divided by the square root of n, or 285 divided by the square root of 25, which is equal to 0.57. And then we want to know the likelihood that we're getting a sample mean greater than 11, so up here. So we need to calculate how many standard errors we are from the mean. Use that to get a z-value out of the z-table. Subtract that from 0.5 to get the area and the tail. So z is equal to x bar. That's our random variable, and that's what we're asking about, minus the mean of the distribution divided by the standard error of the distribution. This was the first application we had for the central limit theorem, so if you want to go look at a few of these, you could look at the first homework after the last test. I believe it's homework assignment 4. You should see some of those on there. But anyway, 11 minus 9.6 over 0.57, and that's going to give you 2.46. So that's the z-value. If you look that up in the table, you will find 0.4931. That's this area, 4931. So the area in the tail is going to be 0.5 minus that, or 0.0069. Okay, I think the biggest problem on this one is I think people just wanted to jump right in and start doing with a hypothesis test or anything, but this is just to find the probability problem. And since it's sample mean, then we're dealing with sampling distributions, which we know are bell-shaped if we take a large enough sample. The other thing is I'm going to recommend on any problem that as you're reading through the problem, make sure you write this information down, that it's the population mean that's 960, and that it's the population standard deviation is 2.85, and we have the sample size. What I had quite a few people doing was putting the center of the distribution as 11 and then doing the 9.6 is what they're computing. But what we're trying to find is the probability of sample mean greater than 11. The population mean is 960. Once you've made this adjustment here to the standard error, this is just like computing a probability under a bell curve from exam 1, just that we have a sampling distribution of x bars now. Okay, hopefully you can see this pretty much right away, that this has two samples, Tozenol and NyQuil, and we have the sample sizes and sample means and sample standard deviations. But when you have a problem with two means, the first question you need to ask yourself is, am I going to pool or not? And I need the variances for that. So the variance for the first one is 14 squared, or 196. And then 16 squared, which is 256. Neither is twice the other. Therefore, we pool. See, I kind of skipped part A here, or actually I didn't get to it. I knew the first thing when I see the two samples is I'm going to get the variances and decide whether to pool or not. The first question is, given the sample size in this problem, which is 25, we have 25 in each, just take the smaller one. So, or you can say NA equal NB equal 25. But really, you just need to take the lower one. In this case, they're the same. So 25. Since 25 is greater than 15, skew is okay. So what do we have to know or assume? What we really have to assume is that there are no outliers and no extreme values. Skew is okay because we're greater than 15. Okay, so once you pool, that affects two things. It affects the degrees of freedom, and when it's pooled, it's NA plus NB minus 2, or 25 plus 25 minus 2 is equal to 48. And then the standard error, Sx bar A minus x bar B, is equal to the square root of NA minus 1 times S squared A. You can put those in either order. I can't remember what I have them on the formula sheet. NB minus 1 S squared B over NA plus NB minus 2 times 1 over NA plus 1 over NB. So that's equal to the square root of 24 times 196 plus 24 times 256 divided by 48, that's the degrees of freedom thing, times 1 over 25 plus 1 over 25. And that all comes out to be 4.25. So that's just the standard error. The confidence interval will be the statistic x bar A minus x bar B plus or minus a t-value times the standard error. So it's going to be 129 minus 134. You can actually, that doesn't make any difference which direction you do those on there. I could have just said x bar A minus x bar B. But I'll leave it the direction it is. That's minus 5. That's just 129 minus 134 is minus 5. Plus or minus the t-value for 48 degrees of freedom and a 95% confidence interval is 2.011. Recheck that here. Yes. 2.011 times 4.25. And taking that all out, okay, I think actually when I did this I made that plus 5, but it doesn't make any difference here. When I did it, it's minus 355 to 13.55, but this way it's going to be minus 13.55 to 3.55. And so that's the confidence interval there. Part C, I'm going to go ahead and answer right here, asks, is this enough evidence to conclude that the population mean is lower? And the answer to that is no. The interval includes 0 and numbers on both sides. So we're saying in this that A is somewhere between about 13 below up to about 3.5 above. So it doesn't necessarily have to be less. It could be the same or or actually more. But this will be enough here. No, the interval includes 0. I'm going to actually scroll this up. You can see here it's looking at the difference between adds. There's 3 of them, and they've been randomly, or 3 types of adds, and we've got 12 per cell here. First thing is, but there's 3 groups, and we have 3 means. You know we're going to be looking at an analysis of variance problem. I'm just going to get the wording out of there just to give me a little bit more space to work this. See how far I can get in the space that's here. Okay, so I'm going to start with knowing that I'm going to need variances here. So those are 2.59, that's just 1.61 squared, and then 2.22 and 5.24. So those are my 3 variances. In a minute, or a couple of minutes here, I'll take the average of those and get MSE. But before I do, I want to write my hypotheses. HO is that the 3 population means are all the same. HR, at least one of the following is true. Mu A not equal to mu B, mu A not equal to mu C, mu B not equal to mu C. I'm going to get my decision rule here, which is going to be reject HO if F test is greater than some value. So we'll need to get degrees of freedom for this. I'll put this down here. The degrees of freedom for the numerator is k minus 1, which is 3 minus 1 is equal to 2. 3, there's 1, 2, 3 groups, that's k. The degrees of freedom for the denominator is total sample size minus k, which is 36. There's 12 in each group, that's a total of 36. It also says 36 in the problem. Minus 3 is 33. And then if you look at the F table, get that up here. If you go to 3 and 33, you'll see the 3, but it just goes to 30 and then 40. I'm just going to pick the one that is goes with the lower degrees of freedom, the higher of the 2 numbers, the 3.3 for 30. So always move up on that table. What that does is it gives you the most conservative value. So if you went down, you could reject at 3.2. We're going to say, well, you have to go all the way up to 3.3. Really, you could interpolate between there and so on, but we're just going to take the most conservative estimate there. And so I think I'll write this here. F test is equal to mean square treatment divided by mean square error. Let's see if I can fit this up here. The MSE, mean square error, is equal to S squared A plus S squared B plus S squared C divided by K. And that's equal to these 3, 2.59 plus 2.22 plus 5.24 divided by 3, and that's equal to 3.35. So I know in the bottom of here I'm going to have 3.35. So for the MSTR, before I can compute that, I'm going to have to get the mean of the means, the mean of the sample mean. Some call that the grand mean, but anyway, x bar A plus x bar B plus x bar C. Get the three sample means, divide them by the number of them, by the number of groups. So we have 17 plus 12 plus 16 divided by 3. That's equal to 15. And then MSTR is equal to NA x bar A minus x bar bar squared. So I'm taking for group A, getting its mean, subtract from the grand mean, weighted by sample size. So that should have been a plus right there. Then do the same thing for NB. X bar B minus x bar bar squared. Then for the third group as well. All of that goes over K minus 1. So we have 12. Let's see, that'll be 17 minus 15 squared plus 12 minus 15 squared plus 12 16 minus 15 squared over 2. And that all comes out to be 84. So 84 divided by 3.35, now I'm back up here. That gives you about 25.07. Well, I'm just going to have to move down here now. 25.07 is greater than 3.3, so reject HO and conclude. I'm just going to arrow over here, conclude that at least one of those is true. And that's part A. Okay. We had some things like this on the homework here, and I think at least in the classroom sections, was pretty clear that I was going to ask something like this on the test. Well, anyway, we have treatment and error. Degrees of freedom with the treatment, degrees of freedom for the error. Okay, so mean square treatment. That's 84. We already computed MSTR. MSE, 3.35. MSE. This was, the F test was 25.07. The degrees of freedom were 2 and 33. This is the numerator and denominator degrees of freedom. And then the sum of squares, If you had gotten just that part that's right there, right now, I would have given you full credit. The sum of squares would be 84 times 2 is 168. And then the mean square times the degrees of freedom for error will give you 110.55. So you've already computed these, already computed that, just fill it in. You already have the degrees of freedom. The only other thing to add to this table is to take the mean square times the degrees of freedom for each one of these. So 84 times 2 is 168, and 335 times 33 is 110.55. Which specific means differ? So we know that at least one of these is true. This is what we had in part A. We rejected HO and we concluded that at least one of these was true. So the information that we have with each one is the difference between corresponding sample means. So X bar A minus X bar B is equal to, get that here, (17 minus 12, which is 5. Then X bar A minus X bar B, I'm sorry, C there, is equal to 17 minus 16. That's equal to 1. And then X bar B minus X bar C is equal to the absolute value of 12 minus 16, or 4. So that's how far apart the sample means are. If we compute HSD, that's the honestly significant difference. It's the cutoff. Whatever value we get here, any one of these differences that are greater than that value will indicate a corresponding difference over here between population means. So that's equal to Q times the square root of MSE over the sample size you used for each group. I'll put the Q in a second here. MSE we already have as 3.35, and there were 12 in each group. So the degrees of freedom for the Q are, for the numerator, just equal to K, or 3. The degrees of freedom for the denominator are total sample size minus K. Same thing it was, it should be DF for each of those. For the denominator, it's the same as we had when we did the F test, or 36 minus 3 is equal to 33. So it's different from the numerator. It's just K, not K minus 1. So if you go to your Q table and you're going to 3, and then you get down to that 30 and 40 thing, just use the one that's the higher of the two. So just go up above the 33 to 30, or below it if you want to think of it that way. But anyway, it's go to the higher of the Q values, the 3.48. That's where we'll go right here. And that all comes out then to be 1.84. So that's bigger than 5 is bigger than 1.84, and 4 is greater than 1.84. So the differences that are the differences between population means that we can be confident about are that mu A is not equal to mu B, and mu B is not equal to mu C. On the other hand, mu A and mu C could be the same. So going back to this, mu B was the normal print. So it looks like, and if you look at just the direction of this here, normal print being the lowest, looks like whether you went with the big heading or the bold print, either one of those led to more responses, and but neither one of those was significantly better than the other. Both better than the normal print, but no real statistical difference between the big headings and the bold print. Okay, so on this one, okay. Okay, a couple of things here is notice that we have before and after, and that we just have one sample of secretaries, the first secretary, the second secretary, the third secretary, and so on. So there is just one sample here. So, you know, we could get X's here. So if we did after minus before, we would have 5 and 8 and so on. So there's just one X here. And so when we do our hypothesis, I'm going to say, did it increase? I'm going to do after minus before as my X. So is the population mean greater than 0? There's not two separate groups, a mu A and a mu B. There's one mean, one group. So the hypothesis is the population mean greater than 0? HO mu is equal to 0. Okay, so you can use your calculator to get the p-value on this. And so what I would do is put all of the before numbers into list 1 of your calculator. Then put all of the after numbers into list 2 of your calculator. So in your calculator you've got L1 and L2 and you've got all these numbers here. Then go to the top and highlight L3 and do L and just type in L2 minus L1. And that's going to fill in this third column with numbers like 5 and 8 and so on. So once you have those in there, this is just going to be a t-test. So you can go stat, tests, t-test. It's a t-test because if we were going to carry this out and do all the calculations, we would have to compute the mean of these numbers, or these. Either way, they're the same things. Then compute the standard deviation of those numbers, and since we would be computing that from a sample, it would be S, the sample standard deviation, which means we need a t-test. So once you get into the t-test thing, at the top you have a choice between inputting either data or statistics, and we have the actual data here. So change your input to data, and then when they ask you about the hypothesis, your mu 0 there, it's going to be 0, and then tell it your data are in list 3, or wherever you put them, wherever you have these values, list 3. And then since you have a greater than, you're going to have greater than there and go down and hit calculate. At any rate, when you do all of that, it's going to give you a t-value and a p-value and all of that. And the p-value that it's going to give you is 0.0039. I have actually rounded it up to 0.004. That would be fine too. Remember, the decision rule is reject HO if p-value is less than whatever your level of significance is. We get 0.0039. That is less than 0.05. Therefore, you should reject HO and conclude mu is greater than 0. Okay, so to draw the sampling distribution for this problem, It's a distribution of x bars. The hypothesized mean is equal to 0. And if you went back and looked at your t-test thing, you would find that x bar was equal to 6.2. And we already knew the p-value was 0.004 or 0039 if you did the rounding there. That's all you needed for that. Again, you could get that x bar off of the calculator from the t-test, or you could go do a stat calc on the variable in L3. So if mu is equal to 0, there's no improvement, then there is a small, a 0.004 chance of observing a sample mean of improvements greater than or equal to the 6.2 that we had in this particular sample. So if HO is true, then we would almost never get a mean as high or higher than the mean that we did actually obtain. Of course, that's a small, and which would lead to a reject HO, which is what we did. Okay. Central limit theorem. Of course, I have this in some other places, but since I'm here and since it's only 9:30, I might as well stick it out and finish this thing up. Okay, so what the central limit theorem says is no matter the shape of a population, and I'm going to draw here two shapes that we have used in here at various places. These each have a mean and a standard deviation for the population. They're a distribution of x's. No matter the shape of the population, if we take all sufficiently large samples that can be drawn from that population, so in the one that we did in class, I had samples like 1 and then a 1, 1 and then a 2, down to 4 and a 4. That original population I started out with 1, 2, 3, 4. And then in the camel-shaped distribution, I had set up that you could set it up to different sample sizes, but I think I set it to take sample size of 100. So basically, I'm going to just say I took sample number 1, sample number 2, sample number 3. Each one of those consisted of 100 numbers. So anyway, you have these samples, and you just keep taking all of them that you can possibly take. Of course, in the original example that I gave you in class, the samples weren't sufficiently large, but at least we could take all the possible samples that could have been drawn from that population. You may recall there were 16 of them, ranging from 1, 1 to 4, 4. In this one, it would take forever, even with a computer, to take all of them in a very large population like that. But anyway, theoretically, take all possible sufficiently large samples that can be drawn from the population, then compute x bar for every one of those samples. So in this one, I had x bar of 1, 1.5 was the X bar for the second one, and then on down to an X bar equal to 4. And so in this one, it just had X bar for the first group, and it dropped a little box down. And remember, this was yellow, and then my boxes were blue. So I just had all the possible samples that you might get. So I have all of these sample means. Then make a sampling distribution of the X bars. That sampling distribution will be a bell curve. You know, in this example, it was an exact bell curve. Of course, we didn't have a large enough sample. But in this one, it was. Or at least it was getting pretty close to one. Close enough that we could use a z-table to calculate probabilities. That sampling distribution will be a bell curve with the mean of the sampling means. This is the distribution of X bars. The mean of that distribution is going to equal the same as the population mean, and the standard error of this distribution, I could have written this over here as well, is equal to the population standard deviation, this one, divided by the square root of n, whatever our sample size was. If it was 100, you divide by the square root of 100. If it was 2, you divide by the square root of 2. So that's the basic part of the sampling distribution. So we have our population and parameters here. And then we have all of our samples, and we compute the statistics from each. It's the distribution of the statistic, in this case the X bar, that follows a bell curve. I'm going to continue on. I'm just going to erase this out and finish the question up. It asked for two more things in this essay, and one of those was the connection to hypothesis testing and confidence intervals, and the other one was to identify what was meant by sufficiently large. So when we do the critical value approach, we'll say something like reject HO if z-test is greater than 1.645. That came from a table that requires a bell curve. And that bell curve is what is guaranteed via the central limit theorem. So because we have the central limit theorem, we can have critical values that we look up in a table. By the way, I'm not going to put it in here, but when we say reject if p-value is less than 0.05, that occurs at the same point as that 1.645. So the central limit theorem also helps us define that cutoff value for the p-value. For confidence intervals, we're going to have statistic. Now let's make this X bar plus or minus z times standard error. Well, the z value here might be a 1.645 or a 1.96. That also came from a table that requires a bell curve, and that's guaranteed by the central limit theorem. So the connection from the central limit theorem to hypothesis testing and confidence intervals has to do with the fact that you need a bell curve in order to use the Z table and something like that for the T tables as well. They are related. But when you use those tables, you're able to use them because the central limit theorem guarantees you that you have that bell curve. Okay, so sample size, what does it mean for a sample to be sufficiently large? If you have a normal population, any n will do. If you have skew, then you need an n of at least 15. If you have outliers, then you need an n of greater than or equal to 40. And if you have extreme values, then you need n greater than or equal to 100. Especially for these last two, this is one of the reasons that I spend quite a bit of time suggesting, and what I do suggest is that any time you work any of these problems with quantitative variables, that you draw box plots. That makes it easy to see if you have outliers or extreme values. Especially easy, by the way, if you use SPSS, which I'm using in some classes, or which I'm using in the web class, will tell you if you have, only shows if you have, it doesn't distinguish between outliers and extreme values. So you kind of have to just know what extreme values are and take a look at that on knowing what you know about those. That is, the outliers are 1.5 IQRs, box widths from the box, and extreme values are 3 IQRs above or below the box and the box plot. And finally, confidence intervals. What does a 95% confidence interval mean? Well, let me reiterate, as I have iterated a few times in class, that 95% is not a statement about one interval. It's a statement about a collection of intervals. It also, and you can see how this is going to drive out of the central limit theorem, if we repeatedly draw sufficiently large samples from a population and construct confidence intervals for every sample, then 95% of those intervals, so we have many, many intervals. Really, by repeatedly, really we're talking about all, just like with the central limit theorem. If we repeatedly draw and get all the sufficiently large samples from the population, I just want to get the idea that there are a lot of intervals. 95% of those intervals will include the true population mean, which you might shorthand as mu true, and 5% of the intervals will not include the true population mean. So graphically, it's going to look something like this. I had written this and left one side short, but I can make it like this. This is a sampling distribution based on the true population mean. We don't know what the true population mean is. We know there is one, and that it has the same center as the sampling distribution of X bar. So that's the sampling distribution based on the true population mean, whatever it is. So we take a sample from the population and construct a confidence interval, and it goes from here to here. That's just one interval, but it says repeatedly. So we take another sample, and we make an interval, and another one, and we make an interval, and another one, and we make an interval. Notice that all of those intervals have the population mean somewhere in the interval. So that's like the 95% of intervals. But 5% are going to be like this. They do not include the true population mean. So the bet we're making with confidence intervals is that when I do intervals like this, that I have a 95 out of 100 chance, or a 19 out of 20 chance of selecting a sample that and constructing a confidence interval that really does include the true population mean. At the same time, I understand that if I were betting on whether or not the interval included the true population mean, having a 95% confidence interval means I'm going to not only win 95% of the time, I'm going to lose the bet 5% of the time. Importantly, the confidence interval, the 95%, isn't about one interval. Each interval either does or does not include the real population mean. Those first four intervals in there, each one of those, once constructed, we may not know it, but it has a 100% chance of covering the true population mean. And the one that I have marked by 5%, that specific one interval, there's a 0% chance that the real population mean is in that interval. The 95% means if we repeat this process, construct many confidence intervals, then 95% of those intervals will include the true population mean.